In this podcast, we're going to talk about the effect of temperature on rate. Generally, as temperature increases, so does the reaction rate. Oops, hidden buttons here. All right, so here we saw that with our glow stick demo during class, and we know that K is temperature dependent. So, the Arrhenius equation describes that relationship. It describes the relationship between the rate and the activation energy. So we're looking at the relationship between K and EA. So K equals A e to the negative EA over RT, where A is the frequency factor, which is a number that represents the likelihood that collisions would occur with the correct orientation for the reaction. So we know that this equation describes how the reaction rate should increase with temperature, that at high temperatures more molecules have the energy required to get over the activation energy barrier, and the number of collisions with the necessary energy increases exponentially with temperature. All right, R is the gas constant that we remember from gas laws. Remember, temperature must always be in Kelvin. Now, if you are to graph the natural log of K versus 1 over the temperature in Kelvin, it will give you a straight line. K is going to be your rate constant. And then it's given, this equation is the y equal mx plus b that you're given from that straight line. So negative EA over R is actually your slope. So we can find EA from the slope as long as we divide by R. All right, so here's an example. The reaction given there was studied at several temperatures, and the following values of K were obtained. And then it wants us to calculate the value of the activation energy for this reaction. All right, so when we're looking at these values, over here in this first column, we're given just regular K, and then in the second column, we were given the temperature in Celsius. So these were the only two things we were initially given. To find the natural log of K, you plug your natural log and then K right here into the calculator, and that's going to give us our Y values for our graph. Okay, and then the temperature right here, we converted from Celsius to Kelvin by adding 273, and then we did 1 over that temperature in Kelvin to get this last column of values. Okay, so we're going to graph now the natural log of K and 1 over time. All right, so here we have done this, and just remember, as I had stated before, that the natural log of K is going to be our Y values, and the, here we go, natural log of K, that's Y, and then 1 over the temperature in Kelvin is going to be your X values, okay? So when you're graphing this, you should get a line like this, and that equation that we saw represents the graph. You see that the R squared value is 0.99999, okay? And we know from that equation that the activation energy over R is going to be our slope here. And our slope is this 1, 2, 2, 3, 6. Okay, so 1, 2, 2, 3, 6. All right, and that's equal to our activation energy over R. R is 8.314, so we can just 8.314 plug that in, cross multiply those numbers. So I've got 1, 2, 2, 3, 6 times 8.314. All right, and that gave me my activation energy, which is 101730. Okay. and that's joules. Okay. All right. It says a reaction is found to have a rate constant of 8.6 times 10 to the negative 1 seconds to the negative 1 at 523 Kelvin and an activation energy of 120.8. What is the value of the rate constant at 270 K? All right. So here is a equation that can help us determine the activation energy with two values for K and two temperatures. Okay, so it's wanting us to find the value of the rate constant at 270 K. All right, so there's our little equation. So we got natural log of K2 over K1. All right, now we need to label the constants, okay, that we have the information we were given at the top. So we have the rate constant at, so we're just going to call this one K1. Okay, that's our first rate. And then there's our T1. It's already in Kelvin, so that's good. Here's our activation energy. And wanting K2. And here's our T2 also in Kelvin. All right, so let's go ahead and plug these in down here into our natural log equation. So we got natural log K2 over K1, which was 8.6 times 10 to the negative 1. So we'll just move that decimal on over. So 0.866. Okay. And then that's equal to the activation energy, which was 120.8. And then R is 8.314. And then we've got 1 over T1, which was 523, minus 1 over 270. All right, so now what you want to do is first you want to do these parentheses. So we've got 1 divided by 523 minus 1 divided by 270 where did freaking Smart Notebook come from? Okay, negative 0.0017. All right, that's the parentheses, and then we got 120.8 divided by 8.314, and that is 14.529. We're going to multiply these, and that gives us negative 0.0247. And then on this side, we have this natural log, K2 over 0.86, and that's equal to that. Now we're going to E this and E that to get rid of these natural logs. So now we have E to that negative 0.0247. So that gives us on this side 0.9756 is equal to K2 over 0.86, and then cross multiply that 0.86 up, and that gives us K2 as 8.4 times 10 to the negative 1. Okay, so that's how you would solve a problem like that. All right, and the last example problem we have is the same thing, and I'm going to leave it for you guys. You get to calculate the activation energy using that same equation, and you have two different temperatures and two different rates.